Let's talk about exponential functions. I want to start with the basics of just looking at 2 to various powers, and let's take them to various simple powers. And so we're going to look at possible exponents 0 through 10, just integers so far. And we're going to look at 2 to those numbers. So 2 to the 0 is 1, 2 to the 1 is 2, 2 to the 2 is 4. One really important thing is that every time you go down one row, the number doubles. So this is really just the doubling numbers, the sequence of what happens if you start with 1 and you double repeatedly. Let's graph that. We want to have a tabular and a graphical understanding right away. And one thing to notice, either from the numbers in the table, the fact that they get big pretty quickly, or the fact that the dots are going off the screen, is that exponential functions grow pretty quickly. When I've got a fixed base, 2, and I take that number to a bunch of different powers, I'm creating an exponential function. And those things get big pretty quickly. In fact, I'm going to have to change the scale on y. Maybe to 100? Oh, maybe not. Maybe even to 1,000. Maybe even a little bit more than that to actually get as far as I want. So finally, I've got a scale that's big enough to accommodate 2 to the 10th, which turns out to be 1,024. But notice one thing that's happened here is that the small values are barely distinguishable from 0. And so this is a very typical thing that we're going to see about exponential functions, is that they go from being very small and then transition and then become very large when you let them go way to the left and way to the right, or even a little bit to the left and a little bit to the right. So that is something that that it grows very fast eventually. And so we have some scale issues, which are that it's hard to get a scale big enough to fit the whole graph without squashing the left-hand sort of tail. So that's going to be a perennial thing to deal with exponential functions. So let's extend that table a little bit. I'm going to go ahead and look at negative values. That's the next thing you learn about when you learn about what exponents mean. We're still going to take the base to be 2, and we're going to look at what happens not only when you take 2 to the 0, 1, 2, 3, but to the -1, the -2, -3. So 2 to the -1, of course, is 1 over 2. 2 to the -2 is 1 over 2 to the 2, or 1/4, or 0.25. And what we see is these numbers get small, and they get small pretty quickly as well. I only have to go out to -10, and this is forced to use scientific notation. So let's see what happens here. If I zoom out, scoot over a bit, then I get the whole graph. But again, if I've got a scale big enough to accommodate that 1024, I can't really even tell the difference between these guys. I have to zoom in quite a bit to see if there's any difference here. I'm really having to zoom in here to see, that's just a little bit above 0. So if we do a scale that's maybe -10, maybe just to 0 in x, but then maybe 0 to 1. Okay, so again, I'm not trying to make the scale really big. I'm just barely getting 2 to the 0 equals 1. And yet, once again, I have this phenomenon that the left-hand tail is very suppressed. And that's just how exponential functions work. Exponential growth, this kind of function that as you increase x, you increase this exponential quantity, that's a metaphor, an imprecisely used metaphor usually, for really rapid growth. It's a very particular kind of growth that we're going to be really focused on, but there's a reason that people often use it just imprecisely as a synonym for, oh, that grows really quickly. So we still have the same scale issues, but really even worse the further you go left and right with this function. Now you can start filling in between these dots. Next thing you learn about when you learn about exponential numbers is things like 2 to the 1/2. Of course, that's just the square root of 2. And so that's going to be, it calculates it as about 1.4. 2 to the 1/4, that's the 4th root of 2, or you could say the square root of the square root of 2, if you want to do that. And so that makes sense. The fractional exponent, that's a in between 1 and the square root is about 1.189. So we could even just do a more detailed table. For example, let's just go by quarters, and let's activate that. Let's say go from 0 to a quarter to a half to 3/4 to 1. We're going to put in a more detailed list of x's, and we're still looking at 2 to all those different x's. What happens when we take a fixed base to a bunch of different powers? Now, again, I'm going to have to play with the scale to get those. Let's say just go from -1 to like 5, and here maybe 0 to 10. Okay. So here again, these dots are going off the screen. On the right-hand side, they're getting pretty small as you go left. But now, if I'm focusing just on a smaller portion and doing a finer grid, the scale issues are not as profound. But what we can see is that all those are lining up in this rather nice curve. And so, in fact, it turns out you can put in any real number for x. It's a little bit weird, actually. It's sort of sophisticated to really pin down the details of what you mean by like 2 to the pi, for example. But you can. And you can always think of it as similar to just taking 2 to a rational number, like 2 to the 3/5 or 2 to the 7/8, something like that. And what we get is the exponential function with base 2. And so this connects the idea of just taking a number and multiplying it by itself repeatedly, takes it a bit further, and gets an idea that it's more like the graphs we're used to, with a function that's not just about the dots. I'll actually take out the dots now, but is more about this continuous function that can give a y value for any x value and still has the same kind of shape, that it grows very quickly on the right when we put in decently large numbers for x, and it decays very quickly on the left, and to see it at all, you have to zoom really way in. So let's do a little bit more with these functions. Let's look at a few very common features here. We still have the scale issues, definitely. The y-intercept, of course. What is that y-intercept? It's 2 to the 0. Oops. It's trying to make that a note. I don't want that to be a note. I want an expression. 2 to the 0, of course, is equal to 1. And that's going to be true for any base. Any base to the 0 is 1, so no matter whether we use 2 or some other bases we'll see in a second, we're going to have that y-intercept 1, unless we put other decorations and modifications and transformations on this function. So that's really important. Notice also that it has a horizontal asymptote. When you go way, way, way left, this fact that the numbers get really, really small, that's called a horizontal asymptote. It says that when you put in x's that are more and more negative, you get y's that are very, very, very close to 0. The horizontal asymptote is y equals 0. So let's try a different base. Do a little comparison before we leave this video. Let's look at 3 to the x. So here we could do a table, but I'll just read off some numbers off the graph. 3 to the 1 is 3. 3 to the 2 is 9. 3 to the 3 is 27. And notice what happens for big numbers. 3 to the x, of course, is bigger than 2 to the x, because you've got a bigger base and you're using the same exponent. Notice, though, that on the left-hand side, 3 to the x is smaller than 2 to the x. For example, 2 to the minus 1 is a half, and 3 to the minus 1 is a third. That's smaller. 2 to the minus 2 is a quarter, and 3 to the minus 2 is 1/9. That's smaller. I like to say that the exponential function, like 2 to the x, it has two jobs. It's to get really big when you go right, and it's to get really small when you go left. And the 3, that was purple curve. The black curve, the 3 to the x, is just doing both jobs better. When you use 3 instead of a 2 for the base, 3 to the x does the job of growing better, and it does the job of decaying better on the left. So we're going to look at a lot of different exponential functions with various different bases. And you just want to think that the bigger the base, the more aggressive the behavior on both sides. Of course, it's going to have even worse scale issues here. It's going off the top very aggressively, very quickly as you go to the right. And if I scale that out to see that, I'm getting really, really, really small looking numbers on the left-hand side. So at 10 to the x, for example, would be even more dramatic. So, okay, let's look at a base between 0 and 1. I'll mention, you could think, well, what if you did a negative base? What if you did like -1 to the x? Problem is you're going to be at least taking -1 to the 1/2, which is I, the square root of -1, and then like -1 to the pi is very tricky and difficult to even to define, even if you have complex numbers. So we're not going to go there. But you can take 1/2 to the x. Let's activate that. Okay. Not too surprisingly, if x is positive, I'm repeatedly multiplying 1/2 by itself. So like 1/2 to the 1 is 1/2, 1/2 to the 2 is 1/4, 1/2 to the 3 is 1/8. Okay, that's getting smaller as you go to the right. If you go to the left, you're taking a fraction, 1/2, to the -1, that's going to be 2. 1/2 to the -2 is going to be 4, so it's going to get big as you go to the left. So notice, if I delete that one as a distraction, it looks like a precisely, exactly flipped version of the 2 to the x graph. Right? So this is more precisely, it's reflected across the y-axis. Okay, wait, we know how to do that in general, right? We know if you start with a curve and any function whatsoever, and you want to flip it across the y-axis, you just apply that same function to -x. Wait, so that means we should be able to take 2 to the x and do 2 to the -x, put the minus in the exponent, and get the same graph. Well, let's see. There's 1/2 to the x, and there's 2 to the -x. They are identical. Okay, and that's not super shocking. Okay, it's because of exponent rules. We know that 1/2 is equal to 2 to the -1, and therefore 1/2 to the x is definitely equal to 2 to the -1 all to the x. And that, of course, is going to be 2 to the -x. So just thinking about rules of exponents, what negative exponents mean, that tells us that these are two different ways of getting what you call a decaying exponential. So that's the thing I'll leave this with. We started out with growing exponential functions, like 2 to the x and 3 to the x. Now we see there's two ways to get a decaying exponential. We'll use both of them. Take a number, in fact 1/2 will be one of our favorite bases sometimes, and just do that to the x, or leave the base to be a number that's bigger than 1 and take it to a negative exponent.